Mic testing. Hello. 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 Mic testing. Mic testing.
Yeah.
Good evening. First of all, thank you all for coming for this KWK talk. I'll talk a few words about ICTS. So ICTS is International Center for Theoretical Sciences with an interdisciplinary center with three goals. One is research, and ICTS contributes to research excellence in the theoretical sciences with high quality faculty, along with floating members of visitors, postdoctoral fellows and students. Then we have research, and another thing is programs. We bring together researchers from all over the world under one roof, and they talk and discuss about challenging questions which poses from the nature. And then we have outreach, that is like us and this talk. And outreach, what we do is we try to bring this science to the civic society. And Kaapi with Curiosity is one of the outreach activities. And this is like a short brief about ICTS for those who are new. So with this, I invite Dr. B.R. Guruprasad, the Director of Planetarium, to welcome all of you.
Respected Professor Subhojoy Gupta and all the faculty and outreach team of ICTS, my own colleagues from JNP, ladies and gentlemen, good afternoon to all of you and welcome you all to this yet another lecture under Kaapi with Curiosity program. As you know very well, Kaapi with Curiosity is a joint program run by Jawaharlal Nehru Planetarium here and International Center for Theoretical Sciences. And just now an introduction was given. And let me tell you in 2-3 sentences about Jawaharlal Nehru Planetarium. Jawaharlal Nehru Planetarium here is one of the premier institutions which is very active in science popularization as well as non-formal science education imparting. Under science popularization program, starting with sky shows, we are running 2 shows called Celestial Fireworks as well as Voyager, the Never-Ending Journey. Very interesting, both of them, both in English and the vernacular Kannada. And we have umpteen programs, like, every Sunday of the month, we have many programs and workshops, teachers programs, students programs, exhibitions and such things. At the same time, as far as non-formal science education is concerned, we have programs at the primary, secondary as well as undergrad levels. We call them as seed, sow and reap programs. So we are active in both non-formal science education as well as science popularization domains. And we collaborate a lot with other institutions. One such collaboration is this Kaapi with Curiosity with an esteemed institution like International Center for Theoretical Sciences. Okay, thank you very much. This was a brief introduction about JNP. Once again, I welcome you all to this joint program and this lecture, especially on a very attractive topic, spaces of shapes. Just now, I was talking to Professor Subhojoy Gupta, as I opined honestly, that though it is not easy to comprehend as we do in the case of physics and chemistry or even biology, mathematics is more of an abstract thing, it requires imagination. But still, I firmly believe in one thing. Mathematics is the language through which nature speaks to us. So it is very important for us to concentrate on mathematics, especially undergrad students, many of them who are here, they can take up a career in mathematics. And we have a good tradition in that. So with this, I end my introduction. And thank you very much. Once again, let me thank Professor Subhojoy Gupta for gracing the occasion and delivering the talk, and he is going to deliver the talk. Thank you. Thank you very much. Sharanya.
I request Professor Rukmini Dey to introduce the speaker.
Good evening, everyone. On behalf of ICTS, I would like to welcome you all to this Kaapi with Curiosity session. Today's speaker is Professor Subhojoy Gupta from Indian Institute of Science in Bangalore, where he has taught since 2015. Subhojoy received his PhD in mathematics from Yale University in 2012. His research lies in low-dimensional geometry and often involves Riemann surfaces and their moduli spaces, drawing on tools from complex analysis and hyperbolic geometry. So today he will, hopefully he will tell us a little bit behind these topics and the spirit and beauty of it. So I would invite Subhojoy now to take the stage. Before that, we would like to present you a little memento from ICTS and JNP. Okay, thank you.
So, thank you for the introduction, and before I begin, I would also like to thank the JNP for hosting this lecture, and to the ICTS outreach team for the invitation to give a talk here. And thank you all for coming. It's a pleasure to be here. My family is here, my friends and students, and some of them are joining in online. So thank you for coming. I'm especially happy here to talk to you about mathematics. I do geometry, and so that's why I have shapes in the title. And today I wanted to tell you an important idea in mathematics, which is very far-reaching. And the idea is quite simple. It is that instead of studying shapes one at a time, one can study all of them at once. Okay, and here at the back here, you see this at the corner, what is the space of current research in mathematics as well. Okay, I'll tell you a result which is within the last 20 years and give you a glimpse of what people are, researchers, mathematicians are working on today. Okay, but that's towards the end. Let me start with something that's more familiar to you, so which is the space of numbers. So numbers are another one of these mathematical objects that mathematicians like to study. Here these are the whole numbers, and these red circles, 0, 1, 2, 3, 4, and so on, and then there's negative numbers, -1, -2, and all. And there are fractions, of course. And all of these numbers, they form a space which is this number line. Okay, so if you take a fraction like 1.5, you can think of it as lying between 1 and 2, let's say the midpoint of 1 and 2 on this line, and so on. So all numbers, each number find its place on the number line, and any two points on the number line represent different numbers. So that's the space that you're already familiar with. You're already also familiar with spaces of pairs of numbers. So if I take two numbers, right, so you can place them as a point on the plane, right? So you can set up the x-axis and a y-axis perpendicular to it, and so you take the first number and sort of go along the x direction, and the second number go along this perpendicular y direction, and you place that number. So the pairs of numbers form a space which is just this plane, right? So that's also familiar to you. You're also familiar with the fact that numbers might represent other objects, right? So we live on a planet, the planet Earth, which is a sphere, which is not exactly a sphere. It's almost a sphere, and we'll come to that later on. And places on Earth are given by a pair of numbers, right? So sort of ignore the poles for the moment, but so there's a latitude and a longitude which tells you where you are on Earth. So these two numbers tells you a place. And so there's a space of places, therefore, which forms a sphere. Okay, and so this is again something that's familiar to you. Here's another such space, a space of colors that you represent on a computer. Okay, so on a computer, if you want to specify a color, you have to give 3 numbers, which is the red, green, and blue intensities, okay, which is in a range 0 to 255. And so the space of these colors forms a cube. You can represent this as a 3-dimensional cube where these 3 axes, the red, green, and blue axes, are the 3 directions in which you can go, right? And so if you start with, let's say, the corner, the value of all these 0, 0, 0, if you move in the red direction, the redness of the color increases, okay? So this tells you what color it represents. And then if you move in the green component increases, and the blue direction, the blueness of the color increases, right? So this is like a space of these colors, right? And so if each point in this cube represents a different color, and as you move around, the color changes, right? So this is also sometimes called parameter spaces, because each color you're describing by these 3 numbers, which are like the parameters, and when you move around, you change these parameters, you're moving around in the space of parameters, right? So this is another such space, which is the space of colors. But today I wanted to tell you about spaces of shapes, okay? And these are some of the shapes that we will encounter today. And for each shape, we will be looking at what describes this shape, right? What numbers describes the shape, and what space do these numbers or parameters form? So let's start with the space of rectangles. Okay, so this is a simple shape that we see all around us. We sometimes carry them in our pockets. So a shape of a rectangle for us, it will not depend on the scaling, right? So this is a rectangle shape, right? This paper, and if I sort of look at it closely, then the length and width will scale by the same factor. So I count that as the same shape. Okay, so that's not a different shape. And I also count things which are rotated to be the same shape, right? So this is just rotated 90 degrees. Well, if I turn my head 90 degrees and look at it, then it's the same shape, right? So I don't count that as a different shape. So what determines the shape then? Well, it's the ratio of the length of the longest side divided by the length of the shortest side. Okay, this is known as the aspect ratio. This is the kind of thing that you see on a TV screen when you're trying to select a screen or something. And so this is a number, right? And so you can think of the space of rectangles as part of the number line. It starts from 1 because at 1 the 2 sides are the same length, right? So and as you go along, the longer side becomes longer and longer. So the 1 you're the square, and as you go along, your rectangle stretches, the shape changes. Okay. So every rectangle shape is a point on this line. So this is the space of rectangles. Okay, and here are some familiar rectangles whose shapes I've plotted. So of course the chessboard is a square, so that's at the point 1, and the square root of 2 is the A4 paper. Okay, this is the usual paper you see in a Xerox shop when you take printouts, right? So this has a special shape because if you fold it up in half, the rectangle you get is actually the same shape as the original one. Okay, so it's just scaled up. Okay, so the shape doesn't change, and this is the square root. This aspect ratio is square root of 2. So let me actually work it out on the board for you. So here's my A4 sheet. Let's say the longer side is A and the shorter side is B, and so the aspect ratio is A divided by B. If I halve it, if I fold along the dotted line, so it becomes, so now the longer side becomes b, so this length doesn't change, but this length becomes half, right? And it turns out here, so the aspect ratio is b divided by a by 2, right? Or you can take 2 on top if you want. And so if you want this equals that, this ratio equals that, well, it just implies, if you just multiply it out, that a squared by b squared is equal to 2, right? And then you take a square root, and you have that the aspect ratio is square root of 2. Okay, so this is the reason why the A4 paper has been chosen to have this shape, so this is a special point in the space of all rectangles. Okay, and you can have other shapes also. There's another famous one which is the golden rectangle, where the aspect ratio is what is known as the golden ratio, and this was sort of known to the Greeks. So I have a few pieces cut out in that golden ratio shape. You can collect them later, and so this has a property that if you sort of cut out a square base which is length equal to the shortest side, then the rectangle that remains has the same shape as the original one. Okay, so this is another special property, and it turns out it is this point in the space of rectangles. And this is just the rectangle I carry around in my pocket. That's my phone. Its aspect ratio approximately 2.1, and I looked it up. This is apparently the tallest building in Bengaluru, and this is approximately a rectangle, and it's aspect ratio approximately 4.6. I'm sure there are taller buildings in the world, but and as you go further down, I'm sure the builders are more and more nervous about building such tall structures. But anyway, these are, so you see rectangles all around you, and in the screen is also rectangle. You can probably place this shape somewhere in this line, which is the space of rectangles. Okay. Now, before I get to the space of all triangles, let me look at the space of isosceles triangles. Okay. So isosceles triangles have a special mirror symmetry, right? So if you look at this dotted line down the center, if you reflect, you think of it as a mirror. If you reflect the left side of the triangle, it goes to the right side, and vice versa, right? So this has a special property that you have two lengths of the triangle are equal, right? Now, once again, we don't care about the scaling. So if I scale this picture, then that's the same triangle, and so you can scale so that the base is 1, and so then what describes the shape of the triangle is just the height. Okay, so this number, which is this distance from the top corner to this base, right? And so once again, in this case, the space of isosceles triangles is part of a number line. This time it starts with 0. So at 0, you're completely collapsed though, right? You're not a triangle, your height is 0. So it's not really in the space. That's why I've marked it with an unfilled circle there. But every positive number, you have a triangle, right? So this, if you're very close to 0, height is small, and so your triangle is squat. If you're further down, your triangle becomes sharp and pointy. So this is the space of isosceles triangles. And once again, you can put familiar isosceles triangles you see around you as points, as these shapes, as points on this number line. This space of isosceles triangles, which is part of the number line, right? So for instance, if you're at half, the point half, remember that the base is height 1. So if you're at half, you're actually a right-angled isosceles triangle. It's like a half of a square cutting along the diagonal. So this angle at the top corner there is 90 degrees. Okay? And if you go further down, at this height, square root of 3 by 2, you're an equilateral triangle, which is another one of these special triangles. And the Eiffel Tower, well, the shape is kind of like that of an isosceles triangle, and its aspect ratio, which I tried to compute, is something like 2.6. Okay, so this is the space of isosceles triangles. So now, the space of all triangles, you have more parameters, okay, because now you have more than one length. You have three lengths of the three sides. They could be different. They could be all different. Of course, you can still scale so that I can assume that the lengths of the sides, call them A, B, C, they add up to 2. Okay, so this I've just chosen 2 to be something convenient. I could have chosen something else also, but let's assume it's 2. So I've just scaled the shape so that the sum of the lengths is equal to 2. So, but there's just still, some degrees of freedom, more than 1 degree of freedom. So the first question one can ask is, when can 3 such lengths, 3 such numbers, positive numbers, form a triangle? Okay, so if I just take positive numbers, these numbers are positive, of course, because they determine lengths of these sides. So if I take 3 positive numbers adding up to 2, when do they form? When is there a triangle whose sides have those lengths, right? So the 3 sides have those lengths. Well, let me tell you the answer. It is when what is called the triangle inequalities are satisfied. So the sum of any 2 sides is bigger than the third. Okay, and it's easy to see. So for example, if I take this one, A plus B is bigger than C. If I take C, the side length C, then C is the shortest distance between the 2 endpoints. Right? And so if you go along A, the side corresponding to A and then B, then you're taking a detour. Right? So you're going a longer distance. So A plus B, the sum of these 2 lengths is always bigger than C, right? And similarly for the other 2 sides. So it turns out that these triangle inequalities are important and necessary. And the question I want to raise is, what are the chances? So suppose I take a strip of paper and this is where the strips of paper that you all have come in, and and don't tear it yet. Let me just show you. So if I tear it into 3 pieces, right? So then what are the chances that these pieces will form a triangle? Well, so if I cut it, so I've already cut it here. So if I look at the pieces here, so if I take the 2 shorter pieces and hold them end to end, it's not longer than the third side, right? So in this case, it's not going to form a triangle, no matter how I try, right? So it's not going to close up, all right? So but sometimes you do get a triangle. So let me just show you one. So in this case, if I take the 2 shorter sides, let's see which one is the shorter ones. Okay, maybe these 2 are the shorter sides. And then look at its length. So these 2 are just holding it together, and so this is longer than the third side. Okay, and so here I will be able to form a triangle because the triangle inequality is satisfied. Okay, so the strips of paper that you have, I've already marked for you some randomly placed notches. Okay, so if you look carefully, maybe some of you won't have it, but so then you have to just cut it randomly. But otherwise, you have to find the notch and you cut it or just tear it at that notch. Okay, and I want to see how many of you can form a triangle and how many of you can't form a triangle. Okay, so you find that those notches on your strip, and cut along them. You get 3 pieces, and then you have to put them. You have to see whether the 2 shorter ones is longer than the third, the longest side. Okay, so that they form a triangle. So okay, so is everybody doing it? So once you've done it, I want to ask, okay, how many of you did get a triangle? Okay, all right. And how many of you didn't get a triangle? So there's a lot more, and we'll see the reason why there are a lot more who didn't get very soon. Okay, so in the next couple of slides. So let's think of it geometrically. So, oh, you got a triangle too. Very good. All right. So, so let's think of it geometrically. So this, yes, no problem. Yes. 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 Yes, that's right. So as I mentioned, yeah, so you're saying why are these true? Well, it's because, see, if you have, so let me do it again on the board. So if you have a triangle, if I take any of the sides, the C, this is a straight line, right? The straight line is the shortest path between 2 points. Okay, so if I look at these 2 points, the end points, C is the shortest path. But if you go along A and then B, you're taking an unnecessary detour if you're trying to reach the fastest. So A plus B would be bigger than C. Okay, this length is bigger than C. Okay, so this is what the triangle inequality is. Okay, and the same thing for the other 2 sides. You just, all right. So, right. So why is it that most of you didn't get a triangle? So let's try to visualize first all the triples of points, all the triples of numbers which add up to 2. Okay, so that forms like this slanting slice in 3-dimensional space. Okay, intersecting the 3 axes at these extreme points. Okay, the 0, 0, 2, 2, 0, 0, 0, 2, 0, where A is 2 and the other 2 are 0, B is 2, the other 2 are 0, and C is 2. So these are the extreme points, and so the solutions of just A plus B plus C equal to 2 forms this white triangle there. And amongst them, so the question is, which of these actually define triangles, right? That was the question which we were after. So we already know the answer, the ones which satisfy the triangle inequality. And that turns out to be this central triangle here. Okay, so you look at the midpoints of these sides of the bigger triangle, and then you connect them up, you get a smaller triangle, the central triangle, and this is where the triangle inequalities are satisfied. And the reason is simple, so let me just do it here. So this central triangle is where these A, B, C, the 3 values, are going between 0 and 1. The bigger one was where they were going between 0 and 2, right? Because the extreme values were, as I said, when A is 2, and the other 2 are 0, etc. But this blue part, the central triangle, is where A, B, and C is between 0 and 1. And why is this the same as satisfying the triangle inequality? Well, it's very simple to see. If let's take C less than 1, then this means that 2 times C is less than 2, right? I've just multiplied both sides by 2. And then if I rearrange, and C is less than 2 minus C, right? I've just rearranged that. But what's 2 minus C? Remember that A plus B plus C is equal to 2. So 2 minus C is A plus B. So you see that A plus B has to be bigger than C. So the triangle inequality here is satisfied. And similarly for A and B, less than 1. So you get all the triangle inequalities satisfied. In fact, these implications go both ways. So it's actually, this blue part is exactly the region where the triangle inequalities are satisfied. Okay, so that's the space where the 3 numbers form a triangle. So now you see yes. Yeah, that's because this is what describes the central part. Okay, so the central part, the blue region, is where instead of varying between 0 and 2, the 3 values go from between 0 and 1. Okay, and that's the same as triangle inequalities. Yes. Yes, that's right. So there's a strict inequality. So these vertices are actually not part of the, so that we're not counted in our space of things. All right. So right. So and now notice that the central triangle, if you compare the central triangle to the bigger triangle, it's exactly 1/4. It's a quarter of the bigger slice, because you can take this, central piece and put these 4 copies, build up the bigger triangle, right? And so around approximately 25% of you would have gotten a triangle, okay? And the rest didn't because of this reason, okay? And now, so this blue central triangle is actually not yet the space of all triangles. Why? Because there are some duplications, okay? So you have here some shapes, so different points corresponding to the same shape, so if you have A, B, and C, 3 numbers somewhere in this blue region, if I change the order of these 3 numbers, you'll find another point in this region, but the shape remains the same. It's just that you've labeled the sides in a different way. All right, and we don't want that. We don't want duplications. We want a space of all triangles where every 2 points are different shapes. And so to make it different, so to account for this, we look at this red portion only, where the coordinates, the 3 coordinates A, B, and C are in increasing order. So they satisfy this, A less than equal to B, less than or equal to C. All right, so this kind of chooses a labeling for you, and so we get rid of that ambiguity, and that red region is the real space of all triangles, what mathematicians call a moduli space. Moduli just means a parameter space. Moduli space is the space of parameters. This time the parameters of all triangles, and to visualize it better, we can look at the shadow on the AB plane. So instead of looking at this slanting picture, the slanting triangle, we can look at its projection to the AB plane, and so this I've drawn it the right way up. So this is the A axis and the B axis, and this purple region is the shadow of that red part. Okay, so this purple region is this moduli space of all triangles, and sort of curiously enough, it itself is also a triangle, right? So it's a triangular shape, and there's one vertex there shown in red. That's like the projection of the center of that big white triangle. That's where all the sides A, B, and C are equal. So that's the equilateral triangle, and these black lines are isosceles triangles. And these edges of the bigger triangle are somewhere where these, one of these values are 0. So that's not really in the part of the space. That if you go closer to the edge, the triangle gets more and more collapsed. Okay, and so anyway, so this is the moduli space of all triangles. And here's another question that you can answer using this picture. You can ask, is it more likely that a randomly chosen point in this, space of all triangles? Yes. Okay.
Direction is different than angle.
Mm-hmm.
Right.
Mm-hmm.
Can you explain this in terms of angle?
Yes. So right. So you can also describe the space of triangles using the interior angles, if that is what you're after. We didn't do that. I wanted to do this experiment with this strip of paper and lengths instead. Okay. So measuring angles with protractors and might take more time. And so yes, so you're absolutely right. You can also have a different description of this moduli space of triangles using the interior angles of a triangle. So that's another way, right? So, but this is the one that I'm describing today here. Yes. Sorry, all the other subspaces? Yes, so I mean, the bigger space, every point here represents a triangle, right? If that's what you're after. So let me show you the, sorry?
not necessary to have only triangles as a part of triangle. It could make it many polygons in a triangle.
Yeah, all right, yes. So right now we're only looking at triangles, the space of triangles, and one can look at spaces of other polygons if that is what you...
No. My point is, it was an answer to his question.
Oh, this question, okay.
He was saying that a triangle can be made of triangles, but my point is, it's not necessary that a triangle be made of a triangle, only there can be many other polygons.
Yeah, that's right, yes. So usually, if you have polygons with many sides, you can cut them up into diagonals into smaller triangles, right? So, yes, that's right. So the triangle is like one of the basic shapes, right? So, yes. A circle.
It's not possible to have a circle in a triangle if I'm right.
Well, yes, you're right. So right now we're looking at just triangles with straight sides and things like that. So we'll come to, if you like circles better, we'll come to, more rounded things soon on one higher dimension. Okay, so, right, so here's the question, that is it more likely that a randomly chosen point in this, space of triangles. I've drawn the bigger labeled space because it's more symmetric. The changing the ordering of these labels, has a threefold symmetry. So is it more likely that a random triangle, randomly chosen point here? So it's based on edge lengths, right? As was already mentioned, not angles or something. Random in terms of edge lengths. Is it more likely that it's acute or obtuse? Okay, so an acute one is where all the angles are less than 90 degrees. All right. So these pointy triangles. And obtuse is one where at least one angle is more than 90 degrees. Right. So so a right angle is sort of in between the two. It's these red triangles here, and so which is more likely, the pointy ones or the obtuse ones? And it turns out that if you look at right-angled triangles in the space of all triangles, it forms these curved lines shown in red. Okay, and these are exactly projections of these parabolas a square plus b square equal to c square. And so you all know the theorem why that's the lengths of the sides. If they satisfy that, then it's a right-angled triangle. It is Pythagoras' theorem, right? So so that forms these red lines. And on the one side of it is the obtuse triangles in the gray, and the other side, the white one, are these acute ones. Okay, and so if you want to compare, you want to see which is more likely, you have to look at we have to compare the areas of this gray part and the white part and see sort of which one is more. Because if I pick a point randomly in this bigger triangle, what are the chances that you'll pick something in the gray part and not in the white part? Okay, so by the way, so this goes back to my title slide. So this red line here represents the right-angled triangles. So these triangles in red are right angle, and the other side of this are the obtuse angle triangles, and they get more and more obtuse, they get more and more flat as you go towards this edge. All right, and on the other side of the red line are acute triangles. So this is sort of go to that picture that we had earlier. So here I've asked the computer to do an experiment of sort of putting points on looking at random triangles and seeing how many of them are obtuse and how many of them are acute. So let me see whether this works. Yes. So these triangles are being chosen randomly, and they're keeping account of how many are obtuse and how many are acute, and plotting the corresponding points in this bigger labeled moduli, this moduli space of labeled triangles. And so you see that some of the obtuse wins out. And if you compute the area of this gray portion, it turns out that the gray portion is indeed more than the acute portion. Okay, it's around 68% of this total area, and then so indeed, if you pick points randomly, around 68 out of 100 of these randomly chosen triangles are obtuse. Okay, so that's one question that answers. Now, you can also compare triangles. So if you take 2 points in this moduli space of triangles, here I've taken this A and B, so they represent two triangles, and you can ask, well, what's the distance between them, right? Things like that, and so you can try to sort of define some notion of a distance and some notion of a best way, an efficient way of getting from one triangle to another. Okay, so I've just drawn the straight line here, but maybe there are other more efficient ways that you can imagine. And then so here if I do the straight line, you can have a family of these triangles, sort of slowly going from that initial triangle to the final triangle. Okay, so yes. 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 That's right. That's right.
If I understand the infusion in the modular space, the grade area is the only set of A and B combination which can form a triangle.
Correct.
Else.
Yes. Yeah. So this. So this region, this bigger thing is actually the shadow of that central blue triangle. Okay, the central triangle. Okay, and so amongst this portion is the one where there is no duplication. So this is the real modular space, but I've just drawn the whole central triangle to be just completely clear. Okay, so that's why the vertices are 1, 0, 1, 1, and 0, 1. The three values go between 0 and 1. Right. So yeah, thank you for the question. All right. So right. So once you have moduli space of shapes. Here it's for triangles, but you can imagine you can form moduli spaces of shape. You can play such games and sort of understand how to compare two shapes and things like that. And that has an application in medical imaging. So here are some scans of the brain, and one can try to compare a scan with a normal brain scan and look at how far it is. Okay, if you define the moduli space of such scans. And there is work done, some applied mathematicians have used the mathematics behind these moduli spaces to try to predict Alzheimer's disease, for instance. And so this is one of the ways that all this subject has applications. Another application is in motion planning. Here's a robotic arm. This is the sort of thing that's used in some manufacturing industries. And these robotic arms have some configurations of shapes, right? So there are some parameters, maybe some angles at the joints or something. And so you're often interested, you're often interested in knowing what's the most efficient way to go from one configuration to another, what uses the least electricity or energy or whatever. And so to answer such questions, you need to look at the moduli space, the space of these configurations, and try to sort of see what's the most efficient distance. And here's an example of a book which is sort of combines these mathematical ideas and sort of in robotics, which deals with this subject. But let me not stop at triangles and yes, of course. Yes. Yes, that changes it, right? So this, so I was, when I said random here, right? So the randomness depends a lot on what you mean by random, right? So yes, so that would change things, okay? So the question was whether if I change my description of this moduli space in terms of angles, interior angles of a triangle instead of lengths, is there a different answer to this question? And so the numbers will change, but I think it's still that it's true that obtuse wins out. But yes, so the notion of randomness depends on our model here. Okay, so that's certainly true. Okay, so so this is what I want to get to. one higher dimension, so surfaces instead of one-dimensional triangles. So then here are a couple of our favorite surfaces. So the surface of a football is a sphere, and surface of a vada is a torus, what the mathematician calls a torus. Right? So now let me look at the first one. So I'm going to look at the space of all these squashed and squeezed and pulled, stretched spheres, right? So these ellipsoids, so each ellipsoid is given by these three numbers, which are the lengths of these axes, all right? So A, B, and C. And of course, I care about only these shapes up to scaling, so I can scale by the longest length axis, and I can arrange by rotation that these ratios which determine the shape satisfy this kind of inequality. So I won't get into this, but let me just show you the picture of what this moduli space then looks like. This is the space of ellipsoids. This looks like a triangle, and every point here corresponds to one of these ellipsoid shapes. At the very top right corner, that vertex is the sphere, okay, where all these lengths, the axis lengths A, B, and C are equal. So let me show you how the rest of it, if you go around, what it looks like. So here's the space again. So at the top right is the sphere. As you go down this orange side, it flattens. Okay, so these are the parameters. One of the parameters is the C by A on this y-axis. So it flattens, and as you go further down and around this side, it gets flatter and flatter. Okay, so this is what the ellipsoid looks like. If you go along the green side, then it becomes, then two of the sides flatten in the same way. So it results in this stretched shape. Okay, and it gets more and more pointier as you go to this corner. Now the bottom side of this space is actually not ellipsoids at all, because you've completely collapsed and you're kind of an ellipse which is it's completely flat. All right, and inside in the interior you have all these axes maybe of different lengths. Okay, so this is the space of ellipsoids, and once again you can plot familiar objects that you see, ellipsoids you see into this space of ellipsoids, and so the Earth is not quite at the very top. Okay, as I said, it's almost a sphere. It's sort of flattened at the poles, so it actually sort of lies on this vertical line. Somewhere in this vertical line in the middle is the shape of an M&M, right? So an M&Ms, and as you go further down, these are flatter, more and more flat. So does anybody know this fish? This is a discus fish. Okay, so it's approximately a flat sort of ellipsoid sort of along this, and so this it turns out in this diagonal, this egg is an emu egg, which is very symmetrical, and you go further down. Anybody know what this is? Yes, that's right. It's this Oumuamua, if I'm pronouncing it correctly. Yes, right. Okay. Yes, it's an interstellar object that had entered the solar system and then went out, and nobody knows what it is. And actually, scientists don't know whether it's this shape. It might also be on this line, but that's one of the guesses. All right, and so that's a more pointy, and I just wanted to plot that. And for a while, I was wondering what enters in the middle somewhere, so ellipsoids which have all three axes different, and until I figured out that watermelons often have that property. Okay, so they're sort of ellipsoids in the interior. All right, and okay, so another application of all this is once you have the spaces of shapes, you can have these morphing paths between them, and this is used in computer graphics. We saw sort of a toy version of it where, sort of between two triangles, if we go in a straight line in moduli space, the shape slowly changes from one to the other. But this is another animation where an orangutan changes into a bird, and this sort of thing in computer graphics, people call them shape correspondences, And you might have seen some of these things in movies as well. All right, but now what I really want to get to are tori. Okay, so these vada-shapes and the space of them. Right, so let me tell you how to build a torus. I'm not going to try to attempt it myself, but there's an animation. You can take a rectangular or a square piece of paper. If you fold two opposite sides and then glue the other two remaining sides, that forms a torus. So let me actually show it again. So you start with this rectangular piece, which is shown flat, and you kind of you glue two opposite sides and then glue the other two. So that's the torus. Now what a mathematician would describe it as is you'll take this rectangle and just mark these pairs of edges that have to be glued in the same color, an arrow. Okay, so here there are these two orange arrows, they have to be glued. Okay, so a point there on that left edge is the same, is identified to be a point exactly diametrically opposite. All right, and the same for the top and bottom faces, bottom edges where you have these green arrows, right? So if you are a ball traveling in a straight line in this torus, once you reach the right edge, you actually continue from the left edge, right? Because the right edge is identified with the left edge, and similarly for the top edge and the bottom edge. So it'll sort of it'll continue its motion. So you're actually moving in a torus. And in fact, here I've chosen this ball to have a slope so that the trajectory forms a closed loop. Okay, and this is called a geodesic loop because you're coming from a straight line. So in geometry, straight lines are called geodesics, and so this forms this kind of more complicated loop. But this is sort of one way of sort of visualizing it in a flat way. All right, so instead of a rectangle, I can also take a parallelogram. Okay, so a parallelogram is this figure where pairs of opposite sides are parallel to each other and of the same length. And so when you glue the left to the right and the top to bottom of the parallelogram, you again get a torus. Okay, and it could be of a different shape. And so what is the space of tori? So the first guess is that you look at the space of parallelograms, right? So how do you define a parallelogram? Well, up to scaling, I can just assume your bottom edge is from 0 to 1. So it's really the top right corner that you can vary. And it turns out that you can vary it anywhere in this upper half plane, everything above this x-axis, which is shown dotted. Okay, so let me actually show you a demo of that. So this is where I can move around this point in the upper half plane on the right, and on the left you can see the shape of the parallelogram that you get. And once again, for each of these shapes, you can identify the top and bottom edges and glue them and glue the right and left edges and get a torus. So the first guess is this. So this is the space of tori. Oops, let me just also show you that if you are in that y-axis, these parallelograms are actually rectangles, and somewhere you're the square torus, and as you go further up, your rectangle stretches. As you get further down towards 0, your rectangle gets squashed. Okay, so if you look at the space of tori, well, if you look at along this y-axis, as you go up, your tori gets squashed or stretched this way, and as you go further down, it gets squashed this way. You never quite reach this bottom point, okay, this dotted line, because there you have sort of infinite stretch. It's like a collapsing happening. Okay, so that's not part of the space, and it turns out that one way to sort of put a geometry on this upper half plane that reflects this property that you can't reach this bottom edge is hyperbolic geometry. It's a non-Euclidean geometry where straight lines, they look like, they either look like these vertical lines like here, or these semicircles which intersect the dotted line at right angles. All right, so these are the geodesic lines, the straight line paths. So straight lines might look curved in hyperbolic geometry. And it happens that if you want to reach this dotted line, moving in fine, so it's a unit speed or something, you can't ever reach it. So this length is infinite. Okay, so this is sort of it is quite suited to this sort of picture where these tori, as you go reach this as you try to reach this dotted line, they get more and more stretched. All right, so this hyperbolic geometry enters, but in fact, there's a little problem because not all points, not all pairs of points give you different shapes. Right? There are duplications. Just like in this bigger labeled space of triangles, there were some duplications. Here there are some duplications as well. If you look at all the complete upper half plane, right? Because for example, if I look at this point at height h and height 1 upon h, well, this torus looks stretched this way and this is squashed this way, but if you sort of turn your head 90 degrees and look at it, it's the same shape, right? So it turns out these tori have the same shape, even though they're at different points in the space. So this is this is one way that there's duplication. Another way, which is slightly more subtle, is if you look at a point. So here I've taken one on this on this y-axis, and then look at the point just 1 unit to the right. Then this new parallelogram actually gives a shape of, when you glue up the opposite sides, gives you a torus which is the same as the original one. Okay, and this is some kind of a cutting and regluing you can do to see that you're actually the same shape. So there's duplication. So what is the actual subset of the upper half plane, which is the correct space of tori? Okay, so no duplications, right? Just like that, that triangle moduli space. So what's the moduli space here? So it turns out that you have to account for these duplications, and these duplications are given by these two operations of inversion and adding 1. All right, and so the correct space is this shaded region here. We'll try to shade it with these dots. This is also called the modular surface. This is the moduli space of tori, where so each pair of points here represents different shapes, and any shape or any torus is actually one of these points in this region. Okay, so this is the modular surface, and this is something that comes up in mathematics quite a lot. And it also has applications. One of the applications for this is an elliptic curve cryptography. So elliptic curves is another name for these tori that mathematicians give tori. So there are elliptic curves defined by number theorists as well, and that is used in elliptic curve cryptography, which is what is used to encrypt your messages that you send in WhatsApp. Okay, this is a screenshot of something that WhatsApp has sent me. It assures me that all my chats and calls, etc., are encrypted, and what they use are these elliptic curves, and these so these tori come in there. Sorry? Yes, that's right. Yes, that's right. So yeah, so the Diffie-Hellman is the sort of the broader scheme of things, and one of the particular way that they actually do it is using elliptic curves over finite fields. Okay, so all right, so but I don't want to stop at tori. So what happens to surfaces of higher genus? Okay, so genus is the number of holes. A torus, surface of a vada has 1 hole. Something like a jalebi has more. So the genus is more. So it turns out that to describe surfaces of higher genus, you have to use this hyperbolic geometry that I alluded to earlier. So instead of looking at parallelogram or something like that, you have to look at polygons, but hyperbolic polygons. So these lines, the sides of this polygon are actually straight in hyperbolic geometry. The straight lines look curved, and so when you glue this octagon here, this hyperbolic octagon, preserving the labels, right? So the labels tell you how to glue them. It turns out you get a genus 2 surface, okay, with these 2 holes, right? And so once again, there is a moduli space of these hyperbolic surfaces. Once you fix a genus here, the genus is 2. In general, you have some genus G bigger than 1. And so you can form a moduli space of hyperbolic surfaces by varying the polygons, right? Just like we varied the parallelograms and we got different tori, you can vary these hyperbolic polygons and get different hyperbolic surfaces. And this moduli space is something that I study in my research. So the shape of this moduli space is quite more complicated, and it has its own geometry, which is very interesting. And I promised you a recent result. This is a discovery, a theorem, which is the 21st century theorem of Mariam Mirzakhani. So you might have heard of her. Mariam Mirzakhani was an Iranian-born mathematician working in the US. She unfortunately passed away a few years ago at the relatively early age of 40. She was a brilliant mathematician who also won the Fields Medal, which is like one of the highest honors a mathematician can receive. And this is one of her results and one of her discoveries that is a celebrated one. Okay, and this theorem says that if you have a hyperbolic surface, X is a hyperbolic surface, one of these things that you get by gluing a hyperbolic polygon of genus at least 2, and she counts the number of geodesic loops, which are simple. Simple means it doesn't cross itself. Okay, so these are these simple geodesic loops, and these might look very complicated on the surface, but she counts the number which has a length at most L, and she showed that it grows like this power L to this power 6g minus 6. Okay, and the proof of this uses the moduli space of hyperbolic surfaces in a very essential way. In fact, the 6g minus 6 is exactly the dimension of the moduli space mg. Okay, and it's quite striking because the statement doesn't involve any moduli space. Okay, the statement is about some hyperbolic surface, okay, a particular hyperbolic surface. But to prove it, prove something like this, you need to look at the space of all hyperbolic surfaces. So this is kind of one of the reflection of this principle in action, the principle that you're looking at spaces of objects might make life more easy. Okay, so right, so this is a kind of a more recent result, and one of the unsolved questions, one of the sort of active areas of research for some people in the field is what does a random hyperbolic surface look like? Just like we were like picking a triangle at random in the space of all triangles, you can try to pick a hyperbolic surface at random in this moduli space mg of hyperbolic surfaces, and so it has suitable notion of random, and you can ask what it looks like, and so you can make this question more precise, and some people are working on this today. All right, so but here's a much more big unsolved question: what is the shape of our universe? Right. So this is one dimension higher. Right. So now we are three-dimensional, shapes. Our universe is three dimensional. I'm sure that some of you would object and say it's actually four-dimensional. Time is the fourth dimension, but let's ignore time for the moment. There are three dimensions where you can sort of move around. And it could be that you are a three-dimensional torus, right? So a three-dimensional torus is one where you start with a cube and identify opposite faces. Just like we were taking a square and sort of identifying opposite sides, now you get one dimension higher. Yeah, so that shape is called a three-torus, or a three-dimensional torus. And so if you're a rocket, going in one direction, just like that billiard ball what was going around in the torus, you might come out. You might go out of this side and come back from the other, right? And so it could be that this is one of the shapes of our universe. So, I mean, we don't know. And here's a kind of a book which talks about some of the possible three-dimensional shapes. This is by Jeffrey Weeks, and this is another one of these unsolved questions. Okay, but I want to end with a question about maybe all this has a lot of everyday applications. Right, so in daily life, you might see many variations of the same shape or the same object, right? And so perhaps you can define your own space of objects, their own moduli space, which might be useful. Okay, so so that's the task that I'll leave you with at the very end. So thank you very much. You can play around with some of these demos that I showed you at this link, and the slides as well are there as a PDF file. So thank you.
Thank you, Professor. So we'll now take questions. I request all of you to be precise, like make the question short. Okay. Yeah, yes, we'll start from here.
Hi.
Hi.
That was very interesting. Thanks a lot. So you spoke about the shape of the universe could be that, I
Right.
forgot the term, yeah. So is it like a like a wormhole kind of a connection due to which it the object comes out of the other plane when it hits the
Right, so it's something similar, right? So whether this side is actually glued to the other one. So it's not perhaps not exactly a wormhole, but wormhole would also sort of change the shape but this is a similar thing where if you go out this way, you still have to travel. So the wormholes, if I understand it correctly, is like shortcuts, right? So you can sort of go from one place suddenly to another. This is also something like that, but somehow the gluing is at the very end of the sort of the universe in some sense, right? So it's sort of these two sides that are identified might be quite far away, right? So
Okay.
yeah, so
Thanks.
similar. Yeah, so that also changes shapes.
Thank you, sir, for the talk. So, my question regarding that question also, that he mentioned that from one place to another place, if the object is going, but universe is, it's accelerating, right? So, how it is possible for this scenario that a object can not switch, but move from one place to another? It might be...
Right, so it could be that it's an expanding three-dimensional torus, right? So it's expanding universe could be a sphere as well, right? So it's like a balloon. If you blow your air into it, and the spots on it might move far apart. That's one of the pictures you might have. But you might also think of a torus-shaped balloon, if you like, right? So where it's something like one of these, what do they call it? You use it while swimming, right? So these tubes, and you can, or even your cycle tubes, I guess, the tires, and so if maybe the universe is like that, where except it's one higher dimension, so three-dimensional torus, and so if you put in, sort of pump it out, it's expanding. So I'm not an astrophysicist, so. But I'm sure that, so it's not ruled out. The fact that it's, a three-dimensional torus, a priori, there's no reason why it can't be this, a three-dimensional torus. Okay, so.
When we make a torus out of a two-dimensional paper, we get a three-dimensional shape.
Mm-hmm.
So if we make the torus with the sides actually glued, would it be like a four-dimensional shape with fourth dimension, a spatial dimension instead of a time dimension?
Right. So you had a good point. So here, right. So if you want to really visualize this three-dimensional torus, you have to somehow go to higher dimensions. But you can avoid that by thinking of it as this picture. Like even the two-dimensional torus, right? So, it's actually just two-dimensional. Of course, if you want to view it like a glued-up object, you have to, do it in 3 dimensions. But you can just view it like this rectangle with the side identifications, right? So it's actually flat. If it's like there are 2 ways of going on this shape. So it's actually two-dimensional. Okay, and so it's a more intrinsic way of viewing this whole space. You don't have to look outside and sort of how it. So a similar thing happens here. So to visualize this, it's better to look at these identifications And because we can't quite go to higher dimensions, right? And so, and look at it from above, right, in some sense. So, yes, this is one way of visualizing a three-dimensional shape, that you view it as a familiar three-dimensional shape. See, the inside is also counted as part of the thing, right? That's why it's 3 dimensions. When I drew this torus, it was really the surface only. Of course, when I said vada, you would actually are interested in the inside of the vada as well, but I was only interested in the sort of the surface of it, right? So, so here it's the inside as well, and one of the ways of viewing a three-dimensional object is to take a familiar shape like this and so do these identifications, like these side identifications or something, so then the shape changes, or add these wormholes or something like that, and then the shape changes. Oh. A glue? Well, I mean, you can just define, so for mathematicians it's easy. You just declare that any point on this side is the same as the point on the other side. Okay, so that's how a mathematician would view it. But of course, if you want to, really, sort of really get going, so even it's difficult even with a piece of paper to actually fold it up to make a torus, because once I do this, then, sort of gluing this edge to that other, I have to really do some complicated bending. But, so mathematicians can avoid that by just declaring these points to be identified, okay? And so you view it as an abstract space, and then, worry about whether it can be done at all later, yeah. Oh, you mean that one higher dimensional thing? Yes, so so if you want to really visualize it as something happening in even higher dimensional things, then there might be some holes or things like that, but you can avoid that just by looking in 3 dimensions and just saying that, these objects are identified. This is all part of part of mathematics called topology, and so topologists use such identifications to define new spaces out of old spaces. Okay, so yeah.
What space is made of by using the analysis of three orders.
Is it possible to?
It's possible for us to make some assumption that we have the empty spaces between 2 objects, right? So my point is, if you can analyze that, maybe we could get to the point what the universe is exactly made.
Oh, so you're saying that we can actually analyze the universe, the observational data, and
No, I mean
yes.
to say, you said 3 torus can be the shape of the universe.
Yes.
And in that case, could we predict that, predict what exactly the universe is made of using mathematical analysis like this?
What exactly it's made of?
Yeah.
Well, no, right now it's just about the shape, about the topology of the universe. So, so I don't know whether it has any implication to what the universe is made of. Maybe you're thinking of dark matter or dark energy or something. So I am not an astrophysicist, so I don't quite know. Yeah. Okay.
So,
Now the point nothing. Now you said the universe could be a three-dimensional cube which is an order. Everywhere where we observe the universe, we find lots of empty space. There are concentrated pockets of matter we can combine galaxies, okay, and they are point together like galaxy cluster or something, but then the space between them is really vast. So now my question is, could we replace and then I will control the understand the universe?
Can you use that fact to try to understand what the shape of the universe is? Yeah, I don't know. I mean, yeah, it's possible that, various observational data. So people have worked on this, by the way, so trying to analyze all this, sort of the data that we receive and all these telescopes and etc., the cosmic microwave background, radiation, all those things. And so there is no evidence so far that is a torus, a three-dimensional torus. But, sorry? Yeah. Yeah, so but it could be other shapes. So I just wanted to tell you one such shape. There are other possible three-dimensional shapes. So, I mean, you can read more about them in this book. Yes.
Planets taking elliptical orbits around the sun. Can you interpret from this perspective?
Right. So, I mean, that's another one of these examples of things that lie in this space of ellipsoids and things like that. So, so there's some galaxies also which are elliptical, which are like ellipsoids. So maybe they also belong somewhere there. And so ellipse is another such shape, right? So which is like a kind of a deformation of a circle in some sense, one of these stretched circle, if you like. So one can try to look at the space of ellipses also, for example, and try to say where all the orbits lie. Yes, so yeah, indeed, this always can come up. I'm sure it comes up in astronomy and things like that as well.
My question is, do all collection of objects classify as moduli spaces? Like if we take collection of, let's say, all 3x3 matrices, or if we take a collection of numbers, let's say all natural numbers or all integers, do they also classify as moduli spaces, or are there certain constraints on what can be classified as moduli spaces and what cannot be?
No, so yeah, it's fairly general. Yes, it's a good question. So what can you actually make spaces out of? So it's fairly general. Yes, so there are moduli spaces of, any object that you can, mathematical object that you can think of, or sort of any object. So that's why it's very flexible. This is actually and it comes up in many parts of mathematics, these spaces of these objects and so on. But one of the things you have to make sure is what you actually mean by a moduli space, right? So when one actually does things, so here the kind of point of view I've taken was that, every shape should be some point in the moduli space, and there should be no duplications, right? Yes, so once you kind of understand, right, so what these objects depend on, what describes the object, right? So here we were describing the object with some set of numbers, right? So you have to sort of ask those questions. What defines the object? And then how do we vary those parameters, right? So yes, so it's very general. Yes, so it's actually an idea one can use in many parts of mathematics and hopefully even in everyday life. So yes.
Sorry, the mic is passed to someone. We'll come to you.
Oh, okay.
Yeah, hi. Thanks for the very nice talk. So I'm from an astrophysics background, so I just want to weigh in on that previous discussion.
Yes.
I think people are talking about the shape or the curvature of the universe.
That's right. Yes.
So I think from observations we can tell if the universe is flat or curved.
Right.
So I think we know it's flat, but I don't know if that is related to this torus idea or not, like which is related to shape, like if curvature and shape, like.
That's a good question. Yes, so it is, so it's tied up.
Right.
So in a very deep way, and in fact, this torus, three-dimensional torus, is actually going to be a flat torus. Okay, yes, so there are connections in three-dimensional topology. One also studies curvature and geometry and things like that, and that there is a rich interplay between these two. Okay. Notions. So, yes.
But just by knowing it's a torus, that doesn't tell us if it is flat or curved, like.
Right. It tells us some things,
but
right?
not.
So,
okay.
But it might not. It could be that it's sort of doesn't have constant curvature or something like that. But but maybe it's varying. There are various sort of subtleties which might not be captured by just knowing it is a three-dimensional.
Thank you.
Yes, yeah, of course, that's how science progresses. Yeah, that's right.
So earlier we looked at how you mentioned that triangles, we describe them in terms of side versus kind of like
Yes.
Canonical notion on that moduli space, which is invariant with respect to description.
No, there's no. Yeah, so triangles, there's no good notion of a measure really which is canonical, right? So I've chose the one with the side lengths, and there was this description of this moduli space as a triangle, and I was using the area there, right? But actually this ties back this question that I asked us was about triangles, whether it's acute and obtuse. It turns out that this question was raised in a kind of a problem book. This is about triangles on the plane, okay, which is kind of infinite, without any normal, sort of. I was scaling it so that the perimeter is 2. And so this problem book in the 19th century that was written by Lewis Carroll. Okay, so you would have heard of Lewis Carroll. He wrote Alice in Wonderland. Okay, and so he was a mathematician, in fact. And one of his, he had written a problem book where one of the problems was this, about a random triangle on a plane. And and he didn't clarify what it meant by random, right? And so over the following, sort of century or more, people have given various answers depending on what the notion of randomness is. This is one such answer, right? So where I've kind of scaled things and using lengths, etc., etc. But yeah, so it depends on what the notion of random is. So very much, yeah. There's no canonical.
So are there spaces where there is such a canonical notion? Are there other moduli spaces where you do have such an invariant measure?
Well, right. So I don't know. Possibly there could be, but yeah, usually there's always some freedom, right, in choosing some. Sort of other measure, and sort of even this space of tori that I was telling you about. I mean, there's actually no. I mean, so this hyperbolic geometry gives you some notion of area, and there's some measure there, but you could choose other things as well. So, yeah.
Can I ask a question?
Yes.
You have this triangle, which is the moduli space of triangles.
Yeah.
So what is the metric on it so that these two sides are infinitely far away?
Yeah, that's a good question. Yeah, I didn't talk about putting geometry on the space. I just talked about the shape.
But what is it called? Is there a familiar metric which is? Well,
I mean, actually, in this case, you can try to, do an analogy with moduli space of hyperbolic surfaces or things like that, or conformal or Riemann surfaces, and have a Teichmuller metric is here as well.
Teichmuller metric. Okay.
So I mean, but yeah, there's no canonical. I mean, you can choose a metric. You can define your favorite distance between points in this moduli space. Okay, so yeah.
Hi. So I'm partly summarizing the understanding for myself, but also thinking of it more from a construction perspective. What you said about taking a parallelogram or quadrilateral and making it into a torus makes sense. But then the more I thought about it, what question I couldn't answer is the outer dimension is obviously going to be larger than the dimension that forms the inner.
No, that's a good point. So that's when you try to visualize it in three-dimensional space.
Right.
But if you just declare, like I did here, that this point is identified with the opposite point, right? So then I don't have to make a worry about lengths at all. I'm not trying to deform it and make it into a torus. I'm just declaring these points the same. Mathematically, this is a torus. Okay, so because it has, so you can, it has this property that a torus has of having genus 1 and so on. So this is indistinguishable from an actual torus that you see in real life, these surface of a vara. But if you view it in real life, then you will have, as you said, things like, some lengths of the outer radius and the inner radius and things like that, which you have to worry about to actually construct it. So yeah, this maybe answers the other question of whether you can actually construct some of these things. So a mathematician, topologist will just say that this side, these sides are identified, and won't worry about actually whether you can bend it and something. We're not bending it in a higher dimensional space. We are just sort of declaring, using this flat picture and declaring the points to be identified. Then the shape changes, and it becomes a torus.
Thank you.
Yeah, thanks. Yes, sure.
One more question we'll take from the audience.
We have the moduli space of a given class of shapes, maybe. The topology on it should be something that one would like to construct so as to ensure, for example, that continuous deformations of shapes should correspond to continuous paths in the moduli space. Similarly, what should be the motivating direction for defining the geometry? So more concretely, in typical examples of moduli spaces studied, what do geodesics in the moduli space?
So what should geodesics look like in the moduli space of shapes, is your question?
In the moduli space of shapes, what do they typically correspond to for the shapes themselves?
For the shapes themselves? Yeah, it depends on how you define. So you can, so these moduli spaces, you can give a geometry, right? So so I just took a straight line here, but you can define some notion of a distance and what's a straight line in that. And it depends. It's on the situation which you want to model, right? So just like those robotic arms, so to go from one configuration to another, you want to minimize something, right? So to get to the most efficient motion. But what that something is depends on the situation. Okay, so right, so there's no single answer which is correct all the time. It depends on the answer, on the setup. Yeah.
Yeah. Now we'll take a few questions from our online audience. Okay. First one will be when WhatsApp generates a new session key, is it just picking a random point on your torus map?
So now you're getting into intricacies of this cryptography, which I'm not an expert in. But yes, so there is a torus, but it's actually defined over a finite field. Okay, so it's not exactly the smooth torus that I showed you a picture of, but it is more like a cloud of points, and there is a particular torus. Defined by an equation which they use in this WhatsApp this elliptic curve cryptography, but yes, so it represents some point in the space of all such tori over finite fields. Yeah.
Another question by Pushtam. Some elliptic curves are insecure. Geometrically, what makes a curve weak on the shape space?
Yes, that's a good question there. I mean, I'm not a cryptographer, so presumably there is some study of what kind of curves, elliptic curves are good for cryptography and things like that, right? So, there is an analogous, sort of picture probably that is relevant, and one can try to study, okay, which parts of this moduli space is good for making these encryption work. Okay, so there might be a study there which I'm not aware of. Yeah.
We'll take one more question. If a quantum computer breaks this encryption, what would that mean? Would that mean if found a shortcut on your shape space? Or is it usually completely different rules?
Well, yes, I mean, again, I'm not a cryptographer, but yes, quantum computing is something that can break some of these encryptions that happen, that we do. So elliptic curve cryptography, I don't think it's immune from that. So it is a genuine worry. It's probably not the same as having shortcuts in the space of tori, but it's something else. Yeah.
Yeah. So with this, we'll wind up. The thing is, it gets recorded.
They may take to break that Diffie-Hellman encryption to decipher it. It may take simply like 120 years. So on that basis, this deciphering and the encryptioning and this mathematics involved in that, it works on that basis, which is impossible thing because we don't know like where we can go. We can launch a rocket to Mars or extraterritorial. We don't know anything, but there is a limitation. We call it as an infinity because we cannot reach to that. We will consider that as an infinity. Here also there is a limitation. Don't know. Maybe it will take 100 years.
Yeah, thank you all. And now I thank Professor Subhojoy for patiently answering all your questions and for the wonderful talk.
Okay, thank you.
So-
Thank you very much.
And one more thing, I would like to take a moment to advertise our next Kaapi with Curiosity. So this will be held in the coming Sunday on the 5th of July. So the speaker is Professor A. Raghuram. He is from the Fordham University, New York, and he will be talking about the story of pi. And you can read the abstract. So it is published outside. While you take the coffee, you can read the abstract there. Do register and come for the next talk. Thank you.
Okay, thank you. There are some golden rectangles here if you want to